Okay. All right. So let's continue. So we're going to be talking about the seminars that each of you has to give at the end of this course as part of the requirements. This is good for you. It's simpler than a test. It's also more fun. It gives an opportunity to everyone to practice, give a little talks. The first thing I need to know, though, is I need to know how many people. Because how many are registered on Moodle, how many show up to class, and how many handed in homework doesn't exactly... all three of those are not the same number. Okay? So, if you're going to give a seminar, send email. Okay? Send me an email. Very simple. I will give seminar. Okay? This way I will know if you are 14 people or 20 people or 10 people. Okay? It will make it easier to arrange things. The seminars are going to be 15 minutes per person. And the seminars are individual, so each person does their own seminar. We're going to have 2 dates, which we're going to give seminars. Those are the dates that were scheduled in the calendar as the exam dates. So when you registered for the course, you saw 2 exam dates. So on those dates, we're going to have a Zoom session. And on each Zoom session, people are going to present. So each person will have their date. There are 2 options. One is the February 28th, and the other one is March 17th. In your email, indicate which do you prefer. If you don't prefer and you don't care, just say, don't mention or don't write anything, and I'll just randomly put you in one of them. But if you prefer one of them, then please tell me what you prefer. I have to say that you must attend both. Okay? This is mandatory. It's part of the assignment. You have to listen to each person. And part of listening will be giving feedback on each seminar. So this is what we did last year, and it worked out very nice. You had to attend all seminars, and for every seminar given at the end, you had to give notes. Okay, so you just had to write notes, and those notes you handed in to me at the end. Okay, so you have to write something interesting, something that you learned from each of the seminars given. Okay, so you must attend both of these dates. Also, out of respect to your peers, it's not nice talking to one person who has his camera off on Zoom. Okay? That's it. Okay, structure. Structure of the seminar. It's a 15-minute seminar. It's not long, so you can't do something too vast. You can't take a paper and explain all of it into depth. So you have to be very focused about what you're going to do in your 15 minutes. And basically, to help you focus, I want you to think about the following structure when you're building and when you're planning what to do. So every presentation needs to have either a question, a very clear question. What was the research question? What were the researchers asking themselves that they want to present, to do? What answer were they after? Okay. Or I wrote here demonstration goal. Okay. Some experiments are basically coming to say, look, we have entered a new regime. Okay, just like the example that I showed you in the previous class. that experiment entered a new regime of the number split peaks, and the experiment was to demonstrate the entering of this new regime, new unexplored regime. Okay, so what was the question and what was the demonstration? This has to be very clear at the beginning of your demonstration. And then you need basically to explain what are the experiment and or theory tools used. So the experimental system that was shown, what was, what is the fundament, the basis of that we're looking at, Jaynes-Cummings model with this addition or that addition, this regime of that model, and so on and so on. But this is a quantum technologies course, so your presentation has to be related to an experiment. It cannot be purely theoretical. It cannot be, here is a new quantum information algorithm. You cannot present Shor's algorithm. This is not acceptable. Okay? You can show an implementation of an algorithm on a certain system, where the focus needs to be, this is a system, this is what they did, this is what they needed to overcome in order to show this. Okay? So you need to focus on the experiment and on the technology being used. Okay, that should be the focus. And 3, you need to show something beyond class. So something beyond what we need in class, but it does need to be far-reaching beyond. Okay, so you can take some discussion that we did on some system, and as I go through cavity QED, I'll mention some of these things, or circuit QED, I'll mention some of these things, but it can be even just, a certain chapter in a book or a sub-chapter in a book that we didn't go into the details and you want to explain. Okay? It can be some variation of some gate that, let's say, we learned. So we learned some gate on trapped ions, and there is some nice variation. So you can take off from that point and show, okay, this paper showed this variation, and I'm going to show this essence. So it doesn't have to be something extravagant, and it needs to be a little bit related so you don't go too much off course, because you have 15 minutes. So the first few minutes, the audience needs to know what you're talking about. If you go completely off course from what we did in the course, you just don't have time to explain it. Okay? So when you're planning, think about something beyond what we did in class, but not too far beyond, so we can all follow and understand. Okay? That's it. 5, I recommend. You don't have to, but it is highly recommended. Show me your plan. Send me an email. I plan to present this paper. I plan to present this and that aspect from this paper. I plan to present this aspect from these 2 papers. Or I plan to present chapter so-and-so sub and this sub-chapter from this book. My plan is to focus on that, okay? It will help you to know if you're in the right direction, and help me tell you to get out of corners that you might not want to get into. Okay? And finally, 6. So this is the seminar. In addition to the seminar, just like we did last year, so you have the seminar, you have to give notes about every other person's seminar, and at the end of the seminar, there will be questions. The questions can be related or not related to the seminar that you give, and your peers can ask questions, and I will ask the questions. The questions that I ask are part of your grade. Okay? And they can be not related at all to the seminar that you give. They are related to the syllabus and what we did in this course. So I'm going to write specifically what you need to know for these questions. Okay? Think of it as a mini oral exam. Okay? Instead of giving you an actual test, this is like a mini oral exam. Not going to be too hard. But basically what you need to know is the basics of quantum information. So that's Nielsen and Chuang. Chapters 1 plus 2. you can exclude 1.44. That's not relevant. And you need to know from the Exploring the Quantum, Serge Haroche book, chapters 2 and 3. This is the basics that we've learned up to now. Plus chapter 5. Chapter 5 is cavity QED. That's what we're going to do now. In chapter 5, you don't need all of chapter 5. So you need 5.2, 5.3, and 5.4. Is that a question or is that someone with a... Okay, there we go. Somebody... Who is that? Okay, anyway. So 5.2, 5.3, and 5.4. You can exclude 5.2.2. You don't need to go into that discussion. So this is cavity QED, all the chapter 5. Okay. And finally, your last homework set. What we're going to do in the last homework set, it's going to be due a week past the end of the semester. So we're going to finish the semester on January 24th. A week after that, you will have to hand in your last homework. That last homework will be similar to the first homework, only to make it simpler. And I think the first part was was a better experience for you, from what I understood. So we're just going to have the first part. So each of you go into pairs again and write a question with a solution and send it to me. Okay? And that will be your final homework for the semester. That homework needs to be related to Jaynes Cummings model and the technologies that we're going to be talking about. Okay? So that's the final homework. I'll put up that assignment on the Moodle so you don't forget. Okay, are there any questions with that, or can we continue?
Shai,
yeah?
the paper, it's going to be like a list of papers that we need to choose from, or
No.
any paper or any examples?
You go on Google Scholar, search. This is why I stated, show me your plan. I think the part of the experience is searching and looking at abstracts, titles, figures, kind of getting your hands dirty on this. Okay, this is part of the experience. And to help guide you to a good paper, this is why it's important to show it to me. But you're free to search whatever you want. If you have a really hard time, again, come to me and I will help you. Okay, I will guide you. I'm not going to leave you stranded like that. But it's part of the experience, I think. I think it's very important.
About the seminar, it may be on any subject from the course?
Again, sorry, I couldn't, the audio was cut off.
The seminar can be on any subject from the course, starting from quantum information up to the technologies?
Yes, yeah, the seminar can be on anything on the course, yeah. Yeah, but it needs to be related to some experiment in some form.
And about the number 6, the oral questions,
yeah.
Up to what level of questions should we expect?
Oh, okay. So it's going to be like basically what I want to know is that you can discuss the subject. Okay, so you might be talking about trapped ions and so on, and trapped ions, there is a relation to the Jaynes Cummings model. And you might be talking about some experiment that is working in some regime, let's say the resonant regime. And then I might ask you something about Jaynes Cummings model, about the dispersive regime, for example. Okay? You don't need to, I'm not going to ask you to calculate anything on the board. I just want to see that you can discuss and you understand the essence of the things. Okay? The essence of the things. It's not like solve this question right now on the board. It's definitely not at that level. It's just to know that you can discuss the physics that we learned about in class. Okay? So don't worry about, it's not.
And it might be irrelevant to the seminar that we give, right?
Yeah, what I did last year is I drew some connection, so I kind of tried to make some connection, but it could be completely unrelated. Yeah, but it's related, of course, to the course, to the material, of course. Okay, all right. So with this, we're going to move to cavity QED. Okay. And for that, what I'm going to do is I'm going to basically assist myself with the Serge Haroche book. Let me share the screen again. So I'm going to utilize the share screen here. Hang on. Can everybody see the screen? Did I share it? Yes? Someone? Raise their hand?
Yeah.
Yeah?
Yes.
Good. All right. No. This is... Okay, so this is 5.2. This is basically where you start with cavity QED. What I'm looking for is this. Okay, so cavity QED. What is cavity QED? So this is a schematic of a setup of cavity QED. And in essence, what you're seeing here, you can see that there's a setup on the screen. Can everybody see my mouse, or maybe I can do like a little, how do I turn on this, the bigger mousey thing? Not annotate, where is that? I can't find the big pointer thing. Never mind. Can you see my mouse? Yeah? Anyone?
Yeah.
Okay, thank you. All right. So what you're seeing here is a schematic of a cavity QED setup. The heart of the thing is this thing marked with a C. That's our main cavity. It is a high Q cavity. It's 2 mirrors. And inside you have the electromagnetic mode. It's actually 2 modes. But an electromagnetic mode that we're going to be coupling to. So the idea is that, think of the Jaynes-Cummings model, and you're going to have atoms that are going to be coming all the way from O on the left side here, and they're going to be flying and interacting as they're flying through with this electromagnetic mode. Okay, and a certain transition in this atom is going to be close to, on resonance, or dispersively, but still close enough to be dispersively coupled to the electromagnetic mode. So as the atom is passing through, we get this Jaynes-Cummings interaction, and the atom flies through and gets detected in the detector D over here. So this is the heart of the thing. So this is the cavity here, and this is where the interaction happens. Now a little bit of details about what is each thing in each section. So this is what we're going to do now. I'm going to explain what is each part and what it looks like. So the idea here is to create, you can see this circle over here with a dot and a circle. And the idea here is to use what are called Rydberg atoms. Rydberg atoms are a very good model to a nucleus and an electron that is orbiting really, really far away. It is almost a classical model. Okay, you can, and you'll see that in this limit, you can actually treat this classically. Okay. These Rydberg atoms, you can create them by taking any atom that has a single valence electron and then exciting it to very, very high n numbers. And then the idea is that you get these circular orbits for these atoms, which have a large dipole moment that can interact with the field. Okay, so let me write essentially these things down and talk a little bit about the properties of these atoms, and then I'll explain part by part what is going on in the setup. So I'll just write the things in big down here, but I'll keep talking over that picture. Okay, but just the main points so you can follow. And everything that I'm telling you, everything that I'm telling you now is written, I think everything, but yeah. 99% of what I'm telling you is written in the book. So you can think of this lesson as a guided reading to this chapter. Okay, and you will see that we've over the course of the last few weeks, we've actually acquired all the tools that you can just sit down and read a book chapter about a certain technology and a certain setup and understand what is going on. Okay. So the idea is to use these Rydberg atoms. Okay, and these Rydberg atoms, RY, Rydberg atoms, they're actually typically rubidium, but any alkali atom works because they have a single valence electron, and then you can excite it to very high levels. Okay, so you want a high excitation. You want a high excitation level, and typically the atoms are excited to n equals 50. I'm using the usual notation of N, L, and M for atoms, just like you saw in previous classes. So you excite to a high level around n equals 50. And there basically, like I say, it looks like some tiny nucleus with a circular orbit, and the orbit is roughly proportional to A naught n squared. Okay? And while there's n, there's a lot of sublevels, degenerate levels, for L and M, the angular, the orbital angular momentum. But if you excite to L equals M equals n minus 1, and you can see it here, basically. Let me show you. So this is the wave function, what you're seeing here, of such a circular level, where L is excited to that level. I think if you go over it, you can see here, this is the wave function of that level. Okay? And you can see in 5.1, this is basically the energy levels. This is what you expect from the regular simple hydrogen model, where you just have the Rydberg constant with some small modifications. Yeah, it says it here. See in the book. See, like I said, guided reading. So it's slightly modified to take into account the structure of the atom. But these are the energy levels, and we can really imagine this as a 1 over r potential. So a nucleus and a 1 over r potential and an electron symmetrically being circled around. Okay, so it's very simple. It's very close to the Bohr model that you're familiar with. So these are the atoms. Now, if you look at the transition frequency of these atoms, so you have C will symbolize circular mode, so you have omega n circular mode. And if we look at the frequency of nc minus n minus 1c, then you can kind of calculate the number. I can write it down, but maybe I don't know where it is on the page, so I'll just write it down. So that's the energy for this level minus n minus 1 squared. And this is approximately 2 Rydberg constant h bar n cubed. And for rubidium, this is on the order of tens of gigahertz. And specifically for n equals 50, which is the levels that are used in these experiments, you're looking at around 50 gigahertz. So this is the scale that we're looking at. Okay, microwave frequencies around 50 gigahertz. It's important to mention that the fine structure plus relativistic corrections, they're on the order of, that they give corrections to this energy on the order of tens of hertz. Okay, so fine structure corrections, they go like n to the fifth, and they give corrections on the order of tens of hertz. And the hyperfine, that's even smaller, that gives corrections 3 orders of magnitude smaller. So hyperfine, that's on the order of 10 to the minus 2 hertz. So those are small corrections that really don't need to be taken into account where we're looking at these atoms. And like I said, the most important thing about these atoms and the fact that they're excited to these high levels is because of the circular motion and because we can treat this almost classically, and you'll see that most of the treatment in this book is basically classical when we're referring to the properties of this atom, is that if you have this electron that's going around in a circle, you get a large dipole moment. And this dipole moment D, and we're using the same symbol D, it's the same D that we had in the Jaynes-Cummings model and in the Rabi model in previous classes. And this D basically comes out to be A naught Q n squared divided by square root of 2. And the larger n is, the larger the dipole moment, the larger the coupling you get to the electromagnetic mode. So you go higher and higher, and then you're able to push yourself further to stronger and stronger interactions. Okay? Of course, as you go higher and higher in levels, what's going to happen to the frequency, our transition frequency? If we're thinking of a transition frequency between, your qubit's going to be n and n minus 1. So what's going to happen to this transition frequency as you go to higher n's?
Smaller.
It's going to get smaller and smaller. So you want to keep in a regime where your transition frequency is not much, much smaller than your temperature. Otherwise, you're starting with a highly mixed state. Okay, and it's harder to initialize. So you want to stay with a roughly low temperature. Okay, otherwise you have to worry about other things. But otherwise, you want to go to high n's to get a large dipole moment, and around 50, where is that? N equals 50. That's a rather optimal number for these circumstances and for these reasons and many other reasons. Another important thing to note is the degeneracy. So we talked about N, L and M, and there's a degeneracy of the L and M levels, which you may think we may not care about, but we care about because of the symmetry of the wave function. Okay? Only for L equals N minus 1 are we going to have this circular orbit of the atom, of the electron around, and we have this nice symmetry. The problem is that the L equals N minus 2 L equals N minus 2 does not have that symmetry. And also the others, they don't have that symmetry, which means that they're going to radiate a lot faster into the environment. Okay, they're going to have higher couplings, higher moments coupling to the environment, and they can decay very fast. And the problem with having these other levels degenerate with this level is that small fluctuations in the electromagnetic field can induce these transitions, and then your lifetime of the atom sitting in this n equals 50 level is going to decay very fast. Basically going to n equals 50, L equals n minus 1, to this level over here, and then fast all the way down and decaying. And that highly shortens the lifetime of the level. And the way to handle this, well, you could say, okay, so let's just try to cancel the fluctuating electric fields that are jumping around and deal with it that way. But that really doesn't work. There's only a limit to how much you can cancel it. And the way to deal with it is to induce a Stark shift. So basically the idea is to apply an electric field. Let me scroll down to the drawing that, there, this one. Okay. The idea is to induce an electric field. And this electric field basically is going to break the degeneracy between this level and these other levels that we don't want. And you want to break the degeneracy enough such that it's larger than the electric field fluctuation. Then if you have small fluctuations, they're not going to induce these detrimental transitions that will shorten your lifetime. They might cause slight dephasing, slight changes of frequency, but that's really minute. Okay, the detrimental effect is these transitions. And if you separate enough, you're going to prevent those. And the idea, which you can read about in this page over here, what is given is basically it's a classical description, because you're thinking of this nucleus and this electron, and you're using its circular symmetry, that it's going around the nucleus, and the electric field is basically applying a force. So it's pulling the electron down a little bit and pushing the nucleus a little bit upwards. Okay? And then you get a small correction to the orbit. And the small correction causes a slight frequency shift. Now, what the calculation is considering here is, where is it? Where does it say it? Should say it somewhere here. Maybe I'll write it down. I don't see it. Basically, what it's considering is a small force, so F. This is our electric force. It is much smaller than F naught. That's defined here over at 5.8. So somewhere here there has to be the smaller sign, but I don't see it. Okay, but you can see here in 510, if you follow the equation, you will get the dipole, the induced dipole, at least to first order, due to the small force F. Okay? And this induced dipole is going to cause a change in the energy. This change in the energy is given here in 511. Okay? And it's a small change. And you can use this effect, so you can use this effect once to break the degeneracy so you don't suffer from these detrimental energy decay effects. But you can also use it as a feature in the sense that you can tune the transition energy of your atom. So if we're thinking about our qubit, right, our qubit has two levels, right? This is n equals 50, right? And this will be n equals 51. Wait, did I do it? Sorry, 51. Doesn't matter. Okay. It doesn't matter. So this transition frequency is now going to be tuned slightly on the order of megahertz, few megahertz. Let me look on the page. Oh wait, I wrote down where it is. There it is, here. You can see what I'm marking. Okay, so you can apply a field, and you can see that you can induce frequency shifts of tens of megahertz using field strength of, several volts per centimeter squared. Okay, and this is a way to tune our qubit. So you can think of, we're going to have our atom qubit, and there's going to be the cavity, the mode, and we can tune it in and out of resonance to be in this regime or in that regime. So that's a very important knob for our experiments. Okay, so you have these electric fields that play the dual role. One, you want to break the degeneracy, so you have a long lifetime. And two, you want to, it gives you a knob to be able to tune the frequency of your atom. Okay. Now, with these atoms, in these high levels, typically the lifetimes for these atoms are on the order of 10 to 100 milliseconds. So that's quite long. Okay. And over here there should be the number for, here I wrote it down. So for Rydberg atoms in the n equals 50 state, it's 36 milliseconds. Okay, this is for the n equals 50 Rydberg atoms. But you have all these numbers, they're hidden somewhere in the text. So that's the lifetime. So these are the atoms, and that's the lifetime. And the next, what I want to do in the, I have 10 minutes. So what I wanted to do now is I wanted to explain how you detect these atoms. Okay, so let me go back to the drawing and show you what's going on, and I'll explain how we detect the atoms. And then next week I'll just go over and show you how with this setup you can see some nice interesting things like, entangling the different atoms that are flying through to the field and with each other. Things like that. So if we go back to the setup, so at least we finished today with understanding what we're seeing in front of us. So you can see here in the setup, this is D, the detector. So once the atom flies, and we'll talk afterwards, if we have time, I'll talk about how to prepare the atoms. But let's talk about the detector first. So the detector, you have these two parallel plates which have an electric field. So you have an electric field gradient, and there's a hole, and over here you have, it's called an ionization detector. Basically the idea is that, you remember we had this Stark shift that was pulling the electron a little bit. But if we apply a strong enough field, what's going to happen to the atom? It's going to ionize. So the electron is going to get pulled apart away from its orbital, and this voltage that you need to apply is going to depend on the energy level which you're sitting at. If you're in n equals 51, you're going to need a lower energy. Okay, you're going to need less energy to throw it completely, to completely ionize the atom. And if you're in n equals 50, you're going to need more energy. And this is the idea behind the detection of the atom. And what you can see over here in figure 5.18, so this is the ionization signal. It's basically the count that you're getting from your detector in an experiment where you first prepare many times the atoms in 50C, and then you draw it, and then you get this dotted line over here. And then you prepare the atoms in 51C, and you get this solid line over here. And the x-axis, this is basically the field across this plate. Okay? And you can see that for the n equals 51, the ionization field is lower. So if you wanted to measure the state of the atom, you'd basically put this around 135, 134 volts per centimeter on the capacitor plate. And if you get a signal, you know you're in your ground state or excited state, depending on how you labeled it. It doesn't really matter that much how you label it. So you get this readout, and the overlap between these two signals, you can there's a small overlap. This is basically your infidelity. Okay, if these two line shapes, if these two shapes were infinitely separate, then you would have a perfectly projective readout. You know if you're in this state or that state. Okay? Since there's some finite overlap, then there is a chance for infidelity. So suppose that you get you put this voltage over here, and you get a readout. You would say, okay, I'm in, my atom was in state 51, but actually there is a small probability that your atom was initialized in 50, and you're just on the tail right over here of the spectra. Okay, and this is the infidelity. Now what you're seeing here, this graph over here, is showing a readout, a single shot readout fidelity of about 90%, which is relatively high. I think you can get higher readout fidelities these days. If you're talking about quantum information and quantum computing applications, you really want to get to 99.9% readout. But this is extremely good. This is a very, very good readout. Okay, 90% is very, very good readout. And this is what you're seeing over here. Okay, so this is the readout and how you detect what state your atom is in. Okay, so back to the setup. So essentially what you're seeing here, so we understood what are the atoms. We haven't talked about the cavity modes yet. I will explain that. I'll explain that next week a little bit. R1 and R2 over here, these are low Q cavities, which basically help us induce coherent fields. So you just drive them. S prime is just, it's a generator. Okay, it's a microwave generator that can apply a coherent state into these low Q cavities. And when we just have a coherent state interacting with our atom, then what do we get? We go back to the beginning of the semester. We have two-level system with a classical field. What does that do? Anyone? No one? It just does simple manipulations on the atom, right? We take it from ground to excited. It gives us the control to rotate the atom along the Bloch sphere. Okay, so this part over here is the part that initializes the atom. I'll go into those details next week. Then they go over here. The atom gets a manipulation, so you can initialize it in whichever state you want on the Bloch sphere. Okay, your two-level system, anywhere you want on the Bloch sphere using the coherent field. Then it goes into here for an interaction, so you get the Jaynes-Cummings interaction with a field that's trapped over here. And then it goes out here for R2 for extra manipulations if you want to rotate it again in one direction or the other direction. And finally it flies over to D to get detected. So this is the essence of the setup. And what I would like you to do is for next week, I want you to read as much as you can 5.2. Okay, so what we're going to be doing next week is we're going to be discussing all of this. We're not going to be discussing the superconducting cavities, just the mirror cavities, so just the Furby-Perot cavities, these ones. So please read 5.2 and also 5.3. As much as you can out of it. We're going to be doing basically 5.2, 0.3, and 0.4 over the next lesson, or I'm going to show you the essence of what is shown in those chapters, and then everything else you can do and complete on your own. All right, so are there any questions about the system? About this, hang on, cavity QED system?
Just to make sure, our final goal is to make a full quantum computer out of this system?
No, that's what I said in the beginning. You're not going to make a quantum computer in the system, but what we're going to show is the essence of the Jaynes-Cummings model, where we're going to see how you can entangle one atom with the other, how you can do like an operation, create a Bell state between two atoms, create maybe a GHZ state between three atoms. So you can basically entangle many, many atoms. In an ideal sense, you can think of it as, if you can create many, many atoms that are entangled, then you can create a cluster state, and eventually you could build a measurement-based quantum computer off of that. There are many reasons why this setup is far from being ideal for that, but you can envision it in that context. But what we're going to focus on is just to show how the atom exchanges quanta with the field. So you'll have an excitation in the atom, it can move it to the field or half move it to the field so they're entangled, and then that field can transfer that quanta into a following atom, and so on and so on. You can stitch those things, and you can actually see the features of the Jaynes-Cummings model coming out of that. So we're going to be looking at that platform from that perspective. We're not going to necessarily be analyzing how you can build a quantum computer out of it. Okay.
Is there a situation where there are multiple atoms inside the cavity, or only one atom at a time?
Yes, there are. You can have them. I hope I will get to it. It's the last thing I planned on this thing. You can send two atoms such that they get into the cavity and interact at the same time. You basically send one and send another faster one, and then they meet up in the cavity and they separate away. And you can see that in the dispersive regime. Sorry, did I cut you off?
I asked, don't you have to do it in order to entangle them, to enter them together into the cavity?
No, what you will see next week is that you can send one, it entangles with a cavity. Now the cavity is a high Q mode. So, it transfers part of the excitation to the cavity. And then the next atom comes along and picks up this excitation, and then these two atoms are entangled. They don't need to go at the same time into the cavity. Okay, that's actually the simpler situation. The situation where they both go at the same time to the cavity is trickier. It's also trickier experimentally, because they can also have interactions through free field and not just through the very, very tiny interaction through free field, but yeah. And you need to time the velocities right also. So experimentally it's harder to bring them together. All right, any other questions? Or we can continue next week. Okay, so we're going to continue with this explanation of cavity QED next week. And then in the second part, we're going to be starting the superconducting qubits part of the course.